Having discussed pushdown automaton and context-free grammars and couple of properties about context-free grammars and so on, let's look at the following two questions. Input as CFG, how do we obtain an equivalent PDA? Similarly, input as PDA, how do we obtain an equivalent CFG? So far what we have seen is, given a language, we know how to construct this context-free grammar if it exists, and we also know how to construct an equivalent PDA. Now what this procedure says is, for a given CFG, how do we obtain an equivalent PDA using this? Similarly, for a given PDA, how do we obtain an equivalent CFG? Okay. So far, our construction of CFG or PDA, they were independent. For example, if you look at the language, say a power n, b power n, where n greater than or equal to 1, when we talk about CFG, we look at the strings in L, and we see that base string is AB, and if you look at the next one, it is AABB, which can be seen like these two are same, these two are same, and when you look at triple A this, so there is a match between this, there is a match between this, there is a match between this, which means if we associate a symbol which generates A whenever B is generated, or B whenever A is generated, and that kind of recursion brings you context-free grammar. S implies AB or S implies ASB. That's all. When we talk about pushdown automaton, we say when we read sequence of A's, you perform push, and when you start reading B, you pop A. Pop when B is read. Correct? And transition will say delta of Q0, comma A. Initial stack symbol is Z0. We say we go to Q1 and push capital A. And then at Q1, we say Q1, comma A. Top symbol is A. Then we push some more. We push one more symbol. So which means with this the first A is read, with this remaining n minus 1 A's are read. But this PDA construction is independent of this CFG. This CFG is independent of this, but they are equivalent. This is also generating this language, this is also generating this language. Now, our question is this: given this, can we obtain PDA from this CFG? Similarly, given a PDA like this, can we obtain a CFG using these transitions? Using these transitions, how do you come up with a context-free grammar? Similarly, given a context-free grammar, how do we come up with the sequence of transitions like this? Fine, so that's the question we are trying to attempt. Okay. Let's look at the first one. Let's look at this language itself. Input as CFG corresponding to the language A power n, B power n. So input as S implies AB and S implies ASB. Language corresponding to this is A power n, B power n. Now we shall see how to obtain an equivalent pushdown automaton. See, it is an equivalent pushdown automaton. So, which means if an arbitrary string is given to us, the way this parses and the way the equivalent PDA parses, and if they are isomorphic to each other, meaning they are one-to-one mapping, then you have actually obtained an equivalent push-down automaton. Okay, so that's the larger message. And this message is true for any arbitrary string. For any arbitrary string, you look at its derivation. Maybe you fix one, say leftmost derivation. See how this grammar generates that. On the similar line, let's construct push-down automaton. So what am I saying? Let's take the input to be AABB. It's an arbitrary string. Let me take this example. How will our derivation be? We start with S, then we say S imply ASB, then we apply this rule one more, then it becomes S implies this, because I want to terminate. So let me apply this. If the input string is say triple A triple B, then we say you take S imply ASB, use this rule again. This becomes ASBB, then take this, then we get this. Okay. Now, just like the way this derivation is done, we want to construct an equivalent push-down automaton, which means this derivation somehow it should be mapped to pushing into the stack and popping out of the stack. So something like when you start with S, it should appear like I should push S onto the stack, and subsequently it is replaced by say ASB. And then you get to see that A will be at the top, below that it is S, below that it is B. Now the top symbol is A. So what is that you should do when you look at A? And after that, when you look at capital S, you are supposed to push that again. Push is production corresponding to that. So the larger message is how do we map these derivations into corresponding transitions or corresponding operations with respect to stack. Fine. So here is the idea. So when we start with S, right? So if you look at this derivation, we start with this S. Then we say S implies ASB. With respect to PDA, what we do is, let's assume from initial symbol is Z0, from that we move to this configuration. From the initial configuration, we push capital S onto the stack. Then what we do, we replace S by this one or this one. So in some sense, we do not know whether to replace S by this or this. So we design a non-deterministic mission. Okay, let's assume I replace S with ASB, which means it is B, on the top S, above that it is A. Okay, so I'm trying to generate this string. Objective is to map this derivation with the PDA construction. Now what I will do, when I see a non-terminal, I replace a non-terminal with its corresponding production. Okay. So if you find A implies alpha, and if A is at the top, replace A by alpha and alpha is a string. It is a string over terminals and non-terminals. You push alpha just like the way you push a string onto the stack. But if it is not a non-terminal, but if it is a terminal, then what we do, we perform pop if top equals terminal. So which means we match this and this, we pop A, then we go to this configuration, is that not B? Yes. Now again top symbol is a non-terminal. Now I will have to replace this non-terminal with alpha. In this case there are two productions. Because we go for a non-deterministic mission, one branch will take this, one branch will take this. Because I want to derive this, let me push this. So it becomes B, then B, followed by A. Now this one and this one there is a match, perform pop, and after that again it is a non-terminal, sorry, it is a terminal, so there is a match, so perform pop. After that it is a terminal, there is a match, so pop. So we stop our procedure. So what is this telling us? For a given CFG and an arbitrary string, the parsing of this, meaning the leftmost derivation tree, is simulated by this equivalent PDA. When I say we construct an equivalent PDA, what is that we are actually doing? We are actually simulating this leftmost derivation using this PDA. Fine. So the idea is to push the start symbol. Then whenever you have terminal at the top, you replace the terminal with what is there on the right. But when you see a terminal on the top, you go for pop. That's all. Two simple rules. One is when you see a non-terminal, go for push, and when you see a terminal, go for pop. But when you see a non-terminal, for example, in this case it is yes, you may find more than one production. So which one you should look for to replace? What we design is a non-deterministic mission. Simply guess and go for the right production. Fine. So with this framework, let's construct the PDA corresponding to the CFG. This PDA is essentially simulating the leftmost derivation for a given string. And string could be anything. For any arbitrary string, one can come up with the leftmost derivation followed by an equivalent PDA as well. Okay, let's formally describe this. Here is the construction. Delta of what we construct as a non-deterministic pushdown automaton. So delta of say Q0 comma, initially without reading anything, what we do is we push the start symbol. Next what we do at this, we need to replace, right? So this is where we have to bring in our simulation part. Okay, so now you are in Q1, the top symbol will be yes. How do you replace yes? That's one. Now you may come across a terminal. If you come across a terminal, you have to go for a pop. So if it is terminal, then it is pop. If it is a non-terminal, go for push, and there may be many productions, right? One has to non-deterministically choose the right production. But when you write the description, you have to write all possible values. When you trace, you have to appropriately choose the right one. Fine. So now the top one is capital S. Now it is non-terminal. So now what we do, we stay at Q1 and push AB Z0. We write all possible values for S. We stay at Q1 and push ASB Z0, which means it is this one in terms of stack. If you see, it is Z0 followed by B, S, at the top it is A. Remember, we are trying to simulate the leftmost derivation. So which means if the non-terminal is capital S, that's our start symbol. So one has to replace S by this or this, but it's a non-deterministic mission. So we do not know whether to go for this or this. We write both. Fine. Now there is no match with the input tape now. Now the match can happen. You are in Q1, you read A, and what is there on the stack is A, then you go for pop. Or you are in Q1 and what is there on the stack is B, then you go for pop. Finally, what will happen? You are at Q1, you have exhausted the input, top symbol is Z0. In that case, you reach the final state and stop. Or you can also empty the stack. Now, this part clearly tells you it is push, of course, and most importantly, non-determinism. This one is pop. Now let's look at AABB. Maybe you take say triple A, triple B. Now the way this string is derived by this grammar, the same thing is being simulated by this. So what it says is the following: you start from Q0 without reading anything, you push this. So which means stack becomes this. It is Z0, on top of it this. Now you have this much. Now I need to choose non-deterministically between this and this. So let me go for this. One branch will explore this, another branch will explore this. Which means you replace this by ASB. This is what you will have. Now top symbol is A, input is A, go for pop. You have to go for pop because the top symbol is a terminal. Only for a non-terminal push is allowed. Now when you pop, what will happen? It becomes Z0 B S. Now it's a non-terminal. Either you have to go for this, go for this. Again, non-deterministically one has to guess. So let me guess this. So I'll replace this. Then it becomes B S A. Fine. Now top symbol is A, and what you see over here is A. So go for a pop. And whenever you see terminal, you simply go for a pop. That's it. Now it is a non-terminal. Non-deterministically choose between these two. Now I'll choose this. Now what will happen? You get BB, B on top of it A. Now topmost symbol is terminal, go for pop. After that, top symbol is terminal, pop, top symbol is terminal, pop, top symbol is terminal, pop. Now at this point in time, you can reach the final state. Fine. So initially we push capital S, then all productions corresponding to the non-terminal we will write using Q1. Okay. And for all terminals we go for a pop, that is also written using Q1. And when input tape is empty, top symbol is Z0, reach the final state and accept. So in fact, this we use to push the start symbol. After that, we use Q1 to write the productions corresponding to all non-terminals. In this case, it is just S. Then we use Q1 to write productions, meaning we write pop corresponding to all terminals. Finally, we accept. Now, this clearly tells you that this one is kind of the way this works is precisely the way you simulate this string with respect to this grammar. Meaning the leftmost derivation is precisely captured through this pushdown automaton. Fine. Let's look at one more example.